Welcome to the fourth session of this differentiation series. In this session, we will continue to demonstrate how to use algebra techniques to evaluate limits. In addition, we will introduce the derivatives of inverse trigonometry functions based on the rules of differentiation along with the general power rule. We will demonstrate 4 worked examples in this session.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything. Welcome to the series of differentiation, and this is the 4th session of this series. Here, example 1 is to evaluate the limit of square root of n plus 3 square root of n minus square root of n minus square root of n as n approaches infinite. To solve this problem, we need to use the algebra technique of multiplying and dividing by its conjugate expression. Hence, the limit is simplified to the limit of 4 square root of n over the sum of square root of n plus 3 square root of n and the square root of n minus square root of n as n approaches infinite. After dividing both numerator and denominator by square root of n, it becomes the limit of 4 over the sum of square root of 1 plus 3 square root of 1 over n and the square root of 1 minus square root of 1 over n as n approaches infinite, which equals 4 over the sum of square root of 1 plus 0 and the square root of 1 minus 0, which is 2. Example 2 shows a hybrid function g of x, which equals f of x plus a sine x all over x when x is not 0. G of x equals a constant a when x equals 0, given that g of x is continuous at the point x equals 0, and f of x is a continuous derivative function, and f of 0 equals 0, and f prime of 0 equals b. The question here is to find the value of a. Since g of x is continuous at x equals 0, g prime of x at the point of 0 equals the limit of f of x plus a sine x all over x as x approaches 0. As it can be observed that both numerator and denominator approaches 0 as x approaches 0. We may use the L'Hopital's rule here, which we haven't introduced. Briefly, L'Hopital's rule tells us if we have an intermediate form 0 over 0 or infinite over infinite, all we need to do is to differentiate the numerator and differentiate the denominator and then take the limit. Hence, the g prime of 0 equals the limit of f prime of x plus a cosine x all over 1, which equals f prime of 0 plus a cosine 0, which equals b plus a. So the constant a equals a plus b. Example 3 is to find the expression of the nth derivative of f of x, where n is greater than or equal to 2, given that f of x has unlimited multiple derivatives and f prime of x equals the square of f of x. Since f prime of x equals the square of f of x, the second derivative of f of x equals 2 f of x times f prime of x. It equals 2 times the cubic of f of x. Accordingly, the third derivative of f of x equals 3 factorial times the square of f of x times f prime of x, which equals 3 factorial times f of x to the 4th. Then the fourth derivative of f of x equals 4 factorial times f of x to the 3rd times f prime of x, which equals 4 factorial times f of x to the 5th, and so on.
Now we assume that the case derivative of f of x equals k factorial times f of x to the power of k plus 1th. And based on that, we try to derive the expression of the k plus 1th derivative of f of x. Accordingly, the k plus 1th derivative of f of x equals the k plus 1 factorial times f of x to the case times the square of f of x, which equals k plus 1 factorial times f of x to the k plus 2th. Hence, the nth derivative of f of x equals n factorial times f of x to the power of n plus 1th. Now let's talk about the general power rule for derivatives, given that y equals u of x, or in parentheses to the nth, where u is a differentiable function of x and n is a rational number. According to chain rule, dy by dx equals n times u of x, or in parentheses to the n minus 1th, times du by dx. The following discussion is about the derivative of trigonometric functions where u of x is differentiable. We have already demonstrated the derivatives of trigonometric functions in previous video. Since the derivative of sine x is cosine x, and the derivative of cosine x equals negative sine x as shown in red here. The derivative of sine u equals cosine u times u prime of x, and the derivative of cosine u equals negative sine u times u prime of x. In the similar manner, we can find the derivative of tangent u, which equals the square of secant u times u prime of x. The derivative of cotangent u equals the negative square of cosecant u times u prime of x. Hence, the derivative of secant u equals secant u tangent u times u prime of x, and the derivative of cosecant u equals negative cosecant u cotangent u times u prime of x. Example 4 is to find the derivatives of inverse trigonometry functions. Since there are 6 trigonometry functions, we need to derive them one at a time. Before doing so, we need to recall the range of these trigonometry functions, which is crucial to the procedure of finding their derivatives. We start with arc sine x, the inverse sine function. Here we assume y equals arc sine x, which implies x equals sine y. Then dy by dx equals the reciprocal of cosine y. Since y is between negative pi over 2 and pi over 2, including both endpoints, the reciprocal of cosine y equals the reciprocal of square root of 1 minus the square of sine y, which is written to the reciprocal of square root of 1 minus x squared. Hence, dy by dx equals the reciprocal of square root of 1 minus x squared. Now let's find the derivative of arc cosine x. Based on the assumption of y equals arc cosine x, x equals cosine y. Hence, dy by dx equals the reciprocal of dx by dy, which equals the reciprocal of negative sine y. Since the range of arc cosine x is between 0 and pi, including both endpoints, the reciprocal of sine y equals the reciprocal of square root of 1 minus the square of cosine y, which is the reciprocal of 1 minus x squared. Hence, the derivative of arc cosine x equals negative 1 over the square root of 1 minus x squared. Here we continue to work on example 4 to find the derivatives of inverse trigonometric functions. Now let's find the derivative of arctangent x. since y equals arctangent x, x equals tangent y. Hence dy by dx equals the reciprocal of dx by dy, which equals 1 over the reciprocal of the square of cosine y, which equals the square of cosine y. Since the range of arctangent x is between negative pi over 2 and pi over 2, excluding both endpoints, the reciprocal of the square of cosine y equals 1 plus the square of tangent y, which equals 1 plus x squared. Hence, the derivative of arctangent x equals the square of cosine y, which equals the reciprocal of 1 plus x squared. As for the arctangent x, since y equals arctangent x, x equals cotangent y. Hence dy by dx equals the reciprocal of dx by dy, which equals negative 1 over the reciprocal of the square of sine y, which equals the negative square of sine y. Since the range of arctangent x is between negative pi over 2 and pi over 2, excluding both endpoints, the reciprocal of the square of sine y equals 1 plus the square of cotangent y, which equals 1 plus x squared. Hence, the derivative of arctangent x equals the negative square of sine y, which equals the negative reciprocal of 1 plus x squared. Here we continue to work on example 4 to find the derivative of arc secant x. Since we assume y equals arc secant x, x equals secant y, as we know dy by dx equals the reciprocal of dx by dy, which equals the reciprocal of tangent y, secant y. Since the range of y is between 0 and pi, including both endpoints, but the point pi over 2, tangent y equals plus or minus of the square root of the square of secant y minus 1, and the plus or minus sign depends on which quadrant y falls into, so we need to discuss about it. When y is greater than or equal to 0 but less than pi over 2, tangent y equals the square root of square of secant y minus 1. Hence, the derivative of arc secant x equals the reciprocal of the product of secant y and the square root of the square of secant y minus 1, which equals the reciprocal of the product of x and the square root of x squared minus 1. When y is greater than pi over 2 but less than or equal to pi, the derivative of arc secant x equals the reciprocal of negative product of secant y and square root of the square of secant y minus 1, which equals the reciprocal of the negative product of x and the square root of x squared minus 1. Based on the above, the expression of the derivative of arc secant x can be combined and simplified to the reciprocal of the product of the modulus x and the square root of x squared minus 1. Here we continue to work on example 4 to find the derivative of arc cosecant x. As we have done with the arc secant x, we here assume y equals arc cosecant x, so x equals cosecant y. Then dy by dx equals the reciprocal of dx by dy, which equals the reciprocal of negative cotangent y cosecant y. Since the range of y is between negative pi over 2 and pi over 2, including both endpoints but the point 0, cotangent y equals plus or minus square root of the square of cosecant y minus 1. And here the plus or minus sign is depend on which quadrant y falls into, so we have to discuss about it. So when y is greater than or equal to negative pi over 2 but less than 0, the derivative of arc cosecant x equals the reciprocal of the product of cosecant y and the square root of the square of cosecant y minus 1, which equals the reciprocal of the product of x and the square root of x squared minus 1. When y is greater than 0 but less than or equal to pi over 2, the derivative of arc cosecant x equals the reciprocal of the negative product of cosecant y and the square root of the square of cosecant y minus 1, which can be written to the reciprocal of the negative product of x and the square root of x squared minus 1. In summary, based on the above, the expression of the derivative of arc cosecant x can be summarized to the reciprocal of the negative product of the modulus x and the square root of x squared minus 1. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.